Hello and welcome back. So in the previous classes we have looked at the first law. We then looked at the first law for a control volume, and we also looked at the conservation of mass and saw how we look at combine both the first law and conservation mass to solve unsteady problems in thermodynamics. We will go on to the second law today. So if we, for example, have a system of this kind where we have a battery and we have a light bulb, we can use the unsteady form of the first law, where we have, for example, that dE by dt is q dot minus w dot. There is no mass exchange here, but there is heat transfer and there could be work done. And if we have only, for example, chemical reactions within the battery and we do not have any potential or kinetic energy and so on, we can replace this by the internal energy U, which is what we were doing. Similarly, we have looked at, for example, a device which is a heat exchanger which has both cold fluid and hot fluid. We wrote the full version of the first law, cancelled out changes in potential and kinetic energy and so on. And if we assume this to be a steady process, and if we assume there is no heat transfer through these walls, and we see that there is no work done except for flow work, which is taken into account in the case of enthalpy, what we saw is that our general form of the equation is something of this kind. So assuming that this is 0, assuming a steady state, this is 0, there is no work done in this, so this is 0, and assuming that kinetic energy and potential energy series changes are 0 or negligible, what we essentially got is something of this form. So we saw that we can write the first law in various ways. And we also did that, for example, for what is shown here, which is a diffuser, where we saw that there is no, this would be a steady process, there is no heat transfer is what we would generally expect. We would expect no work to be done in this case, and if we can ignore changes in potential and kinetic energy, then we see it is an isenthalpic process, the enthalpy is constant. But in general, we would expect kinetic energy changes to be there. There is only one inlet and one outlet, and we are assuming steady state. Then we essentially get something like, so m dots can be cancelled out. So we have the enthalpy at the inlet plus we have the kinetic energy at the inlet, which would be equal to the enthalpy and kinetic energies at the outlets and so on. So we were able to write expressions of this kind. We can also write, for example, expressions for air and fuel in, say, a control volume being converted into products by combustion. So if we have a constant volume, controlled volume or a mass or a system of this kind, then our first law would tell us that, for example, it would say that dE by dt in the rate form would be q dot minus w dot. Since there is no mass entering here or leaving here, if I only have air and fuel inside this and I burn it and I get products, so there is no mi dot or me dot, so those terms would be 0. And what I would see is that if this is a rigid chamber of this kind and there is no shaft work and there is no displacement work, there is no electric magnetic work and so on, then this term would be 0. If I was to insulate this chamber, then this would also be 0. Then I see that essentially there is no change in energy with respect to time, or essentially energy is constant, which is something we can find out. So the first law can tell us something about the products because energy is constant. We know what are the initial reactants and so on. So, if you were to look at the same process happening in a constant volume chamber, sorry, a constant pressure chamber, where I have some piston with some mass and I apply the first law for this, then in this case what I will see is I have the similar kind of expression. Or if I am not looking at the rate expression, if I am assuming things are steady with time, then I can also replace these by Q at W and dE. But of course, I know this is an unsteady process, it goes on for a while and then it stops. But here I would have some amount of PdV work because this piston would move up, and then what I see is that I can write this expression in terms of enthalpies instead of. So, this would be in terms of PdV, and I do not have any heat transfer if I assume that this is perfectly insulated. So, then this would be 0. This is non-zero because I have PdV kind of work here, work against the atmospheric pressure and the weight of the piston. And what I can do is, this would be essentially my internal energy, plus if I take this to the other side, it will become plus PdV, which essentially gives me enthalpy. So, in the previous case where I have a rigid chamber, this E1 for this case is essentially internal energy. So, I can also write this in this form, whereas in this case this will be internal energy and I have this PdV. So, I would essentially get enthalpies as being constant between the initial and the final states. So, if I was to plot this enthalpy versus temperature, this would have some kind of a function. So, if I was at low temperature, I have some kind of enthalpy for the reactants. If the reactants themselves were at a higher temperature, I have a higher temperature for the reactants. I have a different enthalpy for the products. If I consider water to be one of the products, and if I in liquid form, and if I have a higher enthalpy if I have water in the products in the gaseous form. So, when it burns, I would usually have water vapor. If I condense out all of the water vapor, then I would have some other enthalpy for this. And what I will see is that the enthalpy of the reactants and the products are the same, which essentially tells me that after burning this, I get products which have lower enthalpies at some temperature, but after burning this, the temperature here is higher. So, what I would have essentially is products being at some other temperature over here, which has the same enthalpy as the reactants. So, and in this process of combustion, I have some liberation of internal energy which makes this hot, which is usually what we recover as heat and use for whatever processes that we want. I have another example here of a dye mixing in, say, water. So, for example, if you put food coloring into water, it mixes. If I look at this as a control volume, I have two substances which are mixing, and I can write the first law for this. That is, supposing this dye is, there are many dyes where if you put them in water, there is no change in the temperature of the water. So, I can assume that the internal energy does not change. There is no work done. If I just mix these two, it is a constant volume chamber. So, that is also 0, and I would be left with the expression of the form dE is equal to 0. I do not have any work done, I do not have any change in internal energy and so on. So, dE is 0. So, I can tell something about the final state knowing the initial state using the first law. So, essentially the point of showing all of this is that first law gives me a relation between heat and work, and I can write the first law for all of these cases, and I can find out what would be the condition finally knowing the initial condition, or I can find out what should have been the initial condition knowing the final condition. But the first law does not tell me anything about the actual conversion, and this is something which I would like to sort of emphasize, and the analysis of feasibility and direction is not given by the first law. So, if I was to go back to all of these conditions, so let us say I put some dye into water, I leave it for a while. After a while, this dye would have mixed and the entire water would be uniform in green color in this case. But first law is applicable for this case. the first law would also be applicable if I initially had a solution which had a green dye mixed in it, and supposing all of the dye came out separately and formed this collection, and there is no dye in other places, the first law would still be applicable. But I do not see this. So, if I leave a solution of say copper sulphate in water or something like that, and it is a closed chamber, so there is no water evaporating or something like that, I do not see all of this stuff coming out of the water and collecting when it is a dilute solution of this form. Similarly, if I have reactants at a certain temperature, if I burn them, I get some products. So, for example, if I have say methane and I burn it with oxygen, I would expect to get water and carbon dioxide. So, I can also balance this. So, I have 2 moles of oxygen burning with 1 mole of methane. So, I get 1 mole of CO2 and I think I get 2 moles of water, and this is something which happens. If I ignite it, I get this. But if I leave this water and carbon dioxide, I do not get back methane spontaneously. I need to do something else if I want to try to see if I can convert this stuff into methane. So, similarly, I have, for example, this combustor here. I can burn stuff and send it out. If I send in exhaust gases, it does not become fuel and air. If I send in exhaust gases through the rear of this gas turbine here, gas turbine engine here, if I send in, so normally what happens is I have air coming in here, it is compressed, it burns with fuel which is injected here, and then it goes out at exhaust gases. But if I now send in exhaust gases from the reverse direction, it does not become air and fuel and come out in this case. But in all of these cases, even though the reverse does not happen, the first law is valid. So, I can write down the first law and find out something about what would be the energy transfers if the process happened, but the first law itself does not tell me whether the process will happen or not. So, that is essentially one of the drawbacks of the first law, and I have yet another example here. If I have a hot substance, if it is brought in contact with a cold substance, I have heat transfer from the hot substance to the cold substance is something which we see all the time. So, if I have a cup of coffee which is hot, I leave it for a while and the atmosphere around is cold. After a while, I see that the atmosphere and the coffee come to the same temperature. But I do not see the reverse case. So, if I keep a cup of coffee which is at the same temperature the atmosphere and I leave it long enough, I never see this case where the coffee becomes hotter than the atmosphere. So, both of them, if the process happened, first law will tell me how much heat was transferred. So, if for example, I had a cup like this, I had some coffee in it, and if this was at some temperature at say 50 degrees centigrade, and the atmosphere is say at 30 degrees centigrade, if this was heat was transferred out and this finally became at 30, then the amount of heat transferred here I would get as say mc delta T, and I can also apply the first law which tells me that dE for this stuff inside this cup must be equal to Q minus del Q minus del W, or essentially delta E is Q minus W. So, there is no work done in this case because this is, for example, a closed system. If I cover this cup with a lid and I leave it here, there is no work done. So, this would be 0. This would cool down. I can find out how much it cools down, and whatever is that energy is essentially the energy which is lost by this coffee over here when it cools from 50 degrees to the atmospheric temperature. But now, if I had this coffee in this cup, I close the lid, I have it at 30 degrees centigrade, I have the atmosphere also at 30 degrees centigrade. If this coffee became from 30 to 50, then this first law would again be valid, again there is no work done, and I know how much would be the change in energy, and then the heat would transfer in this fashion, the energy of this coffee in the cup would go up and it would get to 50 degrees centigrade. So, whether this is cooling of this coffee or heating by the atmosphere to bring it up in temperature, in both cases the first law is valid. But what we know from experience is this process happens. If I keep hot stuff here, it becomes cooler when the atmosphere is cooler. If the atmosphere and the cup are at the same temperature, I do not see this becoming hotter. Or if, for example, the atmosphere was at a higher temperature of say 40 degrees centigrade, then I do not see this giving out heat and becoming colder. So, if this was at 30 degrees and the atmosphere is at 40, the first law would be valid whether heat was transferred this way or this way. But if this was the case, what I would see is that the atmosphere heats this coffee. So, if it is summer and I keep summer, like for example, I keep cooler stuff, let us say even at say 10 degrees centigrade, I take it out of the fridge and keep let us say a cup of cold coffee, I would expect this to become hotter and become finally at 40 degrees, which is the atmospheric temperature. The first law would still be valid if instead of this becoming warmer, if this became colder and gave out heat and this became lower and lower in temperature. The first law would still be valid, but we do not see such processes happening in nature. So, we do not see spontaneous heat transfer happening from cold to hot substances. We see spontaneous heat transfer happening from a hot substance to a cold substance. The first law would be valid in both directions, but the spontaneous process happens only in one direction. So, the first law is not enough to tell me whether something will happen or not. It tells me that if something happens, I can calculate what would happen, but it does not tell me whether the process would happen or not at all.